Hi folks, welcome to our next lecture in the series on Bode plotting. This is the second lecture. During the first lecture we talked about just some brief introductory material and then went on to discuss the Bode plot of a constant gain, which is a pretty simple endeavor. So for this section what we're going to do is talk about the Bode plot for poles and zeros at the origin. So we're going to start with a zero at the origin. So the transfer function for that is simple. It's just h of s equals s. Something that we'll learn later is that s is the Laplace transform of a derivative, or a differentiator to be more precise, and but we'll get to that down the road. So now if we substitute j omega back in for s, then we just know that this is going to be just j omega, which equals omega at an angle of plus 90 degrees. So it's a simple system here. We know the magnitude is omega and the phase is plus 90 degrees. So we should be able to put that on a graphical plot. So let's go ahead and draw some axes here to deal with. So the magnitude is going to be frequency dependent and the phase is going to be fixed. So first of all, we'll deal with the magnitude. So just draw a simple set of axes here. And this will be logarithmic. Remember, a Bode plot is the gain in decibels and the magnitude, or I'm sorry, the gain is in decibels and the phase, yeah, if I could talk. Remember, for a Bode plot, the magnitude is in decibels, the phase is in degrees, and the frequency is logarithmic. So, and we're going to do frequency in radians per second just to make this simple, but we can also convert that to hertz if it suits our purposes. Okay, so I'm just going to draw some marks here. These are frequencies that are a factor of 10 apart. A factor of 10 is a decade. So let's say this is 0.1 radians per second and this is 1 radian per second. Obviously this frequency is 10 times this frequency, so this is a decade, this span of frequencies. If we go up another decade, we would be at 10 radians per second, and yet another, we would be at 100 radians per second, and so on. Now, one thing to notice on a logarithmic frequency scale, we can go infinitely far to the right, and we can just keep going up by factors of 10 over and over and over. To the left, we can keep going down by factors of 10. But the next marker here would not be 0, but it would be 0.001, or 10 to the minus 2, or 1/100th of a radian per second. And we'd go to 1,000th, 1/10,000th, and so on. We would never get to 0. So we'll never get to DC on a logarithmic frequency plot. And that is an important thing to remember. All right, so the gain here, excuse me, this will jump sometimes. It has to do with the gesture recognition. I can't disable every feature here, so apologize for that when that happens. It's part of my new workflow that isn't perfect either, but I hope it's going to be better than what I've had before. So our gain here is going to be gain in dB. Our frequency is in radians per second. So now let's take a look at this transfer function that we have. All right, so we know that because the magnitude itself, so the magnitude of h of j omega, again, this is no surprise, that just equals omega. And so when omega equals 1, right, what is the gain going to be? Well, no surprise, the gain is 1. Unitless. Now when we convert that to dB, we would say, well, we've got 20 times the log base 10 of 1 equals 0 decibels. So no surprise. So on our plot here, we would mark at 1 radian per second, which is what this is, omega equals 1 radian per second, our gain is going to be 0 dB. So we just put a dot there. Now this is, you don't have to do it this way, you don't have to construct it every time, because this is going to happen the same way every time you have a 0 at the origin. So now if omega equals, let's say, 10 radians per second, right? So omega equal 10 radians per second, then the gain is 10. This is unitless. So 20 times the log base 10 of 10 is 20. So that's going to be 20 dB. So we have to move over to here, and we would put a mark up at plus 20 dB. So now I got to go back over to my frequency axis here and mark some other points on it. So I'm going to say this point right here is plus 20 dB, and so I'll draw a little dotted line out here and over to here. And what if I went to 100 radians per second? Okay, so omega equals 100 radians per second. I don't need to specify that here. Then our gain, unitless, is 100, and our gain 20 times the log base 10 of 100 is going to be, well, the log base 10 of 100 is 2, so times 20, that's going to be 40 dB. So I think I chopped that off a little bit. Right. dB. I can't quite fit that on the edge there. So now I'm going to put another dot over here. I didn't quite leave myself enough room, but it's going to live about right here. Okay, now if I go down to 0.1 radians per second, so we're going in the opposite direction. So I'm going to have omega equals 0.1 radians per second. Well, again, the gain here is just equal to omega, so it's 0.1, unitless. So 20 times the log base 10 of 0.1. Well, the log base 10 of 0.1 is going to be negative 1 times 20 is going to be minus 20 dB. We're going to put one more dot on here, and it's going to be right where I've written this, but that's okay. So we're going to put that right about here, and I'll go ahead and mark on here that this is going to be negative 20 dB. And now I can connect these dots together, and what I'm going to see is I'm going to have a straight line, or it should be straight, at least to the best of my artistic ability. And so it's going to be a line that traverses through all those points, and the slope of that line is plus 20 dB per decade. All right, so that's going to be every zero at the origin is going to have that structure. There's nothing else that can change there. All right, so there's the magnitude. Now if we want to do the phase is really easy here. So we'll go ahead and just write a phase axis here. Again, the frequency axis is the same. It's the log of omega, and this is going to be phase, and this will be in degrees. That's just by default. You don't have to do it that way, but most people think that way anyway, so it's going to be all right. And I'm going to go ahead and mark this here at 90 degrees, and our plot is just going to be a constant, except it won't draw. There it goes. It's going to be a constant at 90 degrees. So there we have the Bode plot, straight line methodology. As a matter of fact, straight line or otherwise, this is what the frequency response of h of s equals s looks like. This isn't really an approximation or anything. This is exactly what it's going to look like. Okay, so now we're going to talk about what happens if we have a pole at the origin instead of a zero at the origin. So if the pole's transfer function is h of s equals 1 over s, and when we substitute in j omega, we get h of j omega equals 1 over j omega. Well, if we look carefully at that, it looks sort of like the structure for the impedance of a capacitor, and so we can immediately say, well, this has a magnitude, it's a complex number with a magnitude of 1 over omega, at an angle of minus 90 degrees. So from that perspective, you're going to say, well, that looks very similar to what we were doing with the 0 at the origin, and you'd be right. In particular, though, the magnitude is the reciprocal. So what that means is that the slope of our gain curve is going to be going in the opposite direction. And the phase is negative 90 instead of plus 90. So first thing what we'll do is we'll evaluate for omega equals 1 radian per second. So for omega equal 1 radian per second, then our gain is just 1 over 1, which is 1, and that corresponds to 0 dB. I think you can do that calculation, right? So if the gain gets larger for omega, for example, equals 10 radians per second, then the gain is going to be 1 over 10, right? It's the reciprocal, and so that's going to be a gain of, it's going to be 20 times the negative 20, 20 times the log base 10 of 10 to the minus 1. So that's going to be negative 20 dB. And if we go the other direction, if we plug in omega equals 0.1, then the gain is actually going to be 1 over that. So the gain is going to be 10, and that is going to correspond to plus 20 dB. So if we draw our axes here, and so I come over here and I say, well, we're going to draw the magnitude in dB, and the frequency is going to be logarithmic. Okay, nothing new here. So let's suppose we make this 0.01, 0.1, 1, 10, let's go out one more, 100. Okay, this is our frequency axis, and this is going to be the gain in decibels. All right, so I'll go ahead and mark, let's call this 20 dB, and let's say this is negative 20 dB. Okay, so I want to mark the point that we have for omega equals 1. So we're going to do this case here. Well, that's going to land right here, 0 dB at 1 radian per second. And if we go to 10 radians per second, we're at negative 20 dB, right? So we would be about right here. And if we went to 0.1 radians per second, we'd be at plus 20 dB. So we're going to be about right here. And again, subject to my artistic skills. So if we connect those dots, we're going to see that this looks like a pretty good straight line. Looks like that. All right, so anyway, the slope of this is negative 20 decibels per decade. Okay, so every time we increase the frequency by a factor of 10, then we are going to decrease the magnitude by a factor of 20 decibels. And if we decrease the frequency by a factor of 10, we will increase the gain by 20 decibels. So again, exactly the opposite of what was happening with the 0 at the origin. All right, so the phase plot, again, very similar to the other one, except opposite in sign. Again, so this is omega. This will be our phase in degrees. And so what we're going to find is if this is negative 90, then our phase is going to be just flat at negative 90 degrees over all frequency. Okay, so the pole and 0 at the origin are fairly simple and easy to work with, and they're the same every time. They always pass through. That is one major point, is they always pass through 1 radian per second in terms of the gain. It always passes through 0 dB at 1 radian per second. All right, now one other facet that we want to talk about is if there are multiple zeros at the origin or multiple poles at the origin. Now there can't be both, right? Because one's in the numerator, one's in the denominator. So if we have, for example, if h of s equals s cubed over s squared, you'd say, well, I've got two zeros at the origin, or three zeros at the origin and two poles at the origin. But the thing is what's going to happen is I'm going to cancel that, and this is just going to drop down to S, right? So this whole thing actually goes away. So this is just going to equal S. So it will equal a single zero at the origin. And obviously if this were flipped upside down, it would be the other way, and I'd have one pole at the origin. But I could, for example, have something that just looks like h of s equals s squared, right? That's valid. So I have actually a repeated zero at the origin, and it's going to, now we're going to have something that looks like, if we want to carry that out, it's going to look like j omega squared. I'm going to have something that looks like omega squared is going to be the magnitude, and the angle is going to be j times j, which is -1. So that gives me, I can either go plus or minus 180. So in this case, we'll just say plus 180 degrees phase. So matter of fact, the phase angle will increase by 90 degrees for every increase in the degree of the exponent for the zero at the origin. And when I have this squared term here, remember if we do the logarithm, right? So when I compute the gain in dB, I'm going to have 20 times the log base 10 of omega squared. Well, that's actually just going to be, right, I can pull this 2 out and just multiply it out front here. So that's going to be 40 times the log base 10 of omega. So instead of the magnitude increasing by 20 dB per decade, it's now going to increase by 40 dB per decade. And of course, if I had 3 zeros at the origin, it would increase by 60 dB per decade, and so on. But it still crosses through 0 dB at 1 radian per second. And so I could have, if I had a h of s equals s cubed, then I would have a gain curve passing through 1 radian per second with a slope of positive 60 dB per decade, and it would have a constant phase of 270 degrees, or negative 90 if you want to write it that way. It just depends, but it would be 3 times 90 degrees, so it would wrap around to 270. All right, so the exact same thing happens, except the sign is inverted for a repeated pole at the origin, right? So if I had h of s equals 1 over, let's do 1 over s cubed, just to make this a little bit different, right? So then what I would have is something that has a magnitude of 1 over omega cubed, and the angle is going to be minus 270 degrees, right? So I'm going to have something that looks like 20 times the log base 10 of 1 over omega cubed. That's actually going to be 20 times the log base 10 of omega to the minus 3 power. And now you can see where I can pull this negative 3 out, and I'm going to say that's equal to negative 60 times the log base 10 of omega. So again, for every decade increase in omega, I'm going to drop now by 60 dB. Up here, for every decade increase in omega, I went up by 20 dB per decade when I had a square, s squared as my transfer function. So that's how poles and zeros at the origin work. And then our next lecture, we're going to move on to what happens when we have simple poles and zeros. So thanks for listening, and look for the next video.